At the end of last time, and I showed you this theorem, and so that explains why Euler's method is good and correct. And today I'm going to return to this general formulation, but I'm going to explain this one with examples so that not too much of the generality is in here. So example is this, and that's what I'm going to copy in here and explain. So we're looking at, I have no key there. We're looking at this particular differential equation with initial values 0 and 0. And 0 is good, so I made it as simple as possible like this. And Zx is actual solution. So how do you know this one has actual solution? Probably no method we have learned will you can actually solve this equation. Then how do you know there's an actual solution? Existence theorem, right? Existence theorem says right hand side is continuous, partials also are continuous, therefore it must have a solution, right? So there is a solution Zx there. Even though we cannot write it down, it exists. So I call it Zx. And differential equation looks like this in the right hand side, and the value of this one tells you how fast it's increasing, right? And all this thing is get down to this inequality to control stuff not growing too much so that I can show that this is close enough. So I have to kind of control this one, and for that one we think about the boxes in here. So here's xy plane. 0, 0 is where it starts, right? And there is this actual solution in there, and I just draw it seems like it's a random box, but I carefully crafted this box so that it works out all nicely. So up there is -1, 1, and over here is +1. So if you look at this box, which I call D, also denoted in mathematics like this, x interval is 0 to 1, right? And this is called Cartesian product, cross symbol, Cartesian product. And y coordinate varies from -2 to +1. You're probably puzzled about that. And negative down here and +1 up there, right? If you write it like this, it indicates a set of all points in between in there. So by setting up nicely like this, I have absolutely, because it's a continuous function, what happens to this value if I choose randomly points inside, sure there's a maximum value in there, so I can call that one m, right? So here is extra specific, so it's 1/2 times x plus y squared, so I can control things. This is called triangle inequality, but it is quite common sense thing. So 1/2 is factored out, x plus y squared. If you add two numbers that could be positive and negative, and then change the sign versus change both number to positive number added, and the latter is always greater than equal to the one that before. So here's 1/2. So if I change the absolute value of x plus absolute value of y squared, you change the individual thing positive and add, it's gonna probably not have a cancellation, so it's usually bigger, right? So we have a slightly bigger one, and that's all we need. X grows between 0 and 1, so that's absolutely less than 1. Y varies from -1 to +1, so y squared will always be less than 1 as well. Because 1 plus 1 times 1/2, so it's 1 here. So I guarantee that if you choose any point in here and stick it into this formula, you're guaranteed that it's going to be always less than 1. All right? So it's kind of controlled. That f of x shows up a lot in our calculation. That never grows. That it's never bigger than 1 if you're staying in this box. Okay? So that's one of the reasons why we care about this one. If this is really difficult to calculate, any number that is greater than this maximum value will work. Any number that bounds it. And next thing it says, so the purpose of this box is to get some control on this slope or rate of change, or that one in there. And h is we're starting from here and arriving there in x equals 1. Maybe this is actual solution. And we're going to use Euler's method and to see how different they are. So we're going from 0 to 1, and I'm dividing everything into n pieces, right? Hope this makes sense. H equals 1 over n. So, and yn is the number generated by Euler's method after you're doing n steps. So if you go by 1 over n times, you arrive at exactly here x equals 1, whatever the yn value over here is. maybe yn will arrive at here, something like this. As a straight line. Make sense? And this theorem guarantees that that value yn in actual solution, distance between these two things, is less than h, which is this value approaches 0, m2 divided by m1 e to the m1 minus 1. m1 is any number that is greater than partial with respect to xy. Let's compute that partial. What is the partial of that one, fy? 1/2 0 plus 2y, right? So that's just y in there. So how is this fy grows within that box if it is just simply y, absolute value of y? Y varies from 0 to 1, 0 to negative 1. So absolute value will be always less than 1, right? So I can choose that m1 to be 1. So how much is this partial derivative of fy is growing? That's this part. And they're saying that number m1 is involved in there. So there's m1. What's m2? Is this quantity that's going to show up when we analyze it. It's 1/2 of what is fx? It's 1/2 times 1. And what about fy? We calculated already that was just y there, right? Was that correct? I think it's somewhere there. If you calculate it's y. Times this whole f of xy is 1/2 times x plus y squared. 1/2 is common. You factor out 1/4. 1 plus, this is out. So if you multiply, you have xy. If you multiply there is a square, just the y to the third. And this one, m2, is the maximum value of how this one is growing. So if I put absolute value around it, that's altogether is this one, 1/4 out there, absolute value of 1 plus xy plus y cubed. Right? So if it's three number added together and then it's changed the sign versus if I write, if I add individual thing as a positive number, of course, this quantity is going to be bigger than before. So what is this quantity here? 1/4. So 1. What is the maximum value of x times y? The largest x value is 1. Largest absolute value of y is 1. So it's a 1, 2, right? How about y cubed? That's 1. If you cube it, it's all still inside 1. So it's 1. So it's a 3/4. That's the number they're talking about. So that goes in there. Let's calculate this one then. H is 1 over n, right? What is m2? m2 is calculated here as 3/4. That m2 here is maximum or anything larger than this value here. So it's a 3/4. m1 was this one here, 1, so I don't have to write it. 3/4. m1 was 1, so e minus 1. Okay? So this theorem guarantees that this is actual solution, and if you repeat Euler's method n times, after you're dividing into n pieces, you arrive here at 1. The difference between these two things is going to be less than this quantity. So I tried n equals 0.1. No, n equals 10. So then dividing this one into 10 pieces. I think it has that. Maybe it's there. Maybe I forgot to name it. I don't think it's synced correctly. So I don't have the number, but I kind of remember, I think that was 0.17. Yeah. So try that. Maybe that is a 0.17 or something like that. It's pretty accurate. And if you go 100, and you can see that error level is going down dramatically. There's nothing is happening, only n is varying. So if you chop into more and more pieces, this approaches 0, right? Absolutely. That means this Euler's method will be closer and closer to these actual solutions. Yes? Do you have a question? What is this number? That's actual solution, right? Okay. That's actual solution. And this is our Euler's method after you repeat it n times, if you divide it n pieces. Right. Purpose of this whole thing is that you don't have the actual solution written down, and you are doing Euler's method because it's fast enough, And then this guarantees that without knowing what this one, you can see that in the solution, without knowing what z1 is, we can still tell mathematically and for sure that your approximation to the actual solution is less than this quantity. Yeah, so it tells you how accurate your approximation is without even knowing what the solution is. So it makes you really curious. How can that possible? You don't know the solution, but you still can say that this is up to what point is accurate, things like that. All right, so that's what the statement is about. This one is there to have some get rid of the technical difficulty, just to control on what is happening to f of x, y, and there is that thing in there. All right, I hope this statement makes sense. It gives you an upper bound to control the error. All right, let me explain it further. Here is this thing about that box. Let me get that box again. Let me go back to that box there. Maybe I'm going to redraw it. It's already messed up. So we have already calculated that m. So this is a box, D. And m was f of xy, y prime, f of xy. And we saw that f of xy in that box is always less than 1. That was our choice of n. That means your rate of change is always less than 1. So if you start from 0, 0, right, that's the initial value. When you go to the right with the Euler's method, you cannot increase more than 1, right? I think it's quite intuitive. So if you maximum growth is allowed is 1, right? If you always grow by 1, don't you think is y equals 1 is the best way you can do, y equals x? Is that right? You can't go any more than that. This is a constantly growing, the maximum possibility. This is m, slope m, right? You can't grow any more than that. Or you can grow the negative number because it's absolute value. If you go down, you cannot go below -1 slope. Your Euler's method is trapped in between in here. Intuitively, I think that makes sense, right? But if you use intuition and you're so sure this is true, and next day and wake up, maybe you find a different thing, and that's why mathematicians set out the statement clearly like this and try to give a clear explanation, which is called proof. All right, so let's see if this statement is absolutely true. So I set out a statement like this. So what I'm saying here is that we start from y0 here, and next point here, as you divide it, is somewhere. You think about this lines, but it's all trapped in between these two dotted lines. That's what I'm claiming. So here's a statement to test that, and this is your first exercise. You can answer intuitively, just a little bit better than, oh, that grows like this, therefore it can't happen. A little bit better than that, to write down some mathematical argument that explains better. So suppose xk, yk is below or on that y equals x, or in between, that's y equals in between in here. And xk plus 1, yk plus 1 happen to be outside this two dotted line, either above y equals x or below y equals -x. That makes sense? If that happens, what I just claimed is wrong, correct? I said every point xk, yk is trapped in between these two dotted line. If there's this point like this, one is inside and the other one is outside, eventually it happens, but there will be a moment where if this is last one is inside this region, here's the next one is outside. It should happen at some point. So we pin down to that one in there. Think about why this is wrong. Does the question make sense? If I have a point here, xk, yk, I'm going to call that pk. Next one is pk plus 1, right? It was out there like this, pk plus 1. What's wrong with this information? It's an exercise. You write it down. I think it was sufficient time. But let's hear Jack's idea. What's idea, Jack? Yeah, slope of this thing is what? Yeah, it seems like if it is, if it is 1, it should be parallel to this dotted line, don't you think? Right, so we will never meet that dotted line if it is parallel. If anything above must be, the slope greater than 1. If it is somewhere down here, like that, this slope must be less than -1, right? Anytime that happens, one point is inside and one point is outside, the slope of that one will be greater than 1 or less than -1. Okay? Was that still intuitive? Yeah. So let's compute that. Here's a mathematical. That's a correct answer. Here's a mathematical answer to what is the slope between these two things. Here's a yk plus 1 equals yk is h times f of xk, yk, right? Is yk plus 1 minus yk divided by h. And that's the slope there, right? Don't you think? That's the slope between these 2 points. Because the x coordinate between these 2 points is always h, so that's h down there. That's a run part. And rise part is yk plus 1 minus yk, right? What is that equal to? F of xk yk, right? And you know that this whole thing is supposed to be less than or equal to 1. But if it exceeds there, it's clearly greater than 1. That's nonsense. So it has to be inside there, yes. In general, we don't have this condition, but I looked at the right size of the button and crafted the equation correctly so that numbers involved in the boundary of the boxes is simple and easy. So it's trapped in there. So no matter what you do, how many times you divide it, you're trapped in between these two lines, right? Okay. So all this f of x, k, y is trapped in there. The second one is that zx also, absolute value of zx is also trapped in between these two lines, absolute value of x. Up there is a positive x, down there is negative x, and this zx is actual solution. This is not like 1 by 1, this is actual solution. The best way to understand this one is looking at this differential equation, which is like this. Zx in there, if you stick it in there. And best analysis is using this integral from 0 to, let me choose a t because I'm doing definite integral. If I integrate it from 0 to x, z prime of t dt, that's the best one. Left hand side is antiderivative of z prime of x is zx, of course, right? Minus z0, is that right? That's fundamental theorem of calculus. And right hand side, I'm just going to keep it that way, but I'm going to put the absolute values around. Integral is a Riemann sum. Riemann sum is a sum of things, right? So you add them all up and changing it to the positive number versus you change all these individual sum n to a positive, then add them all up, and then it's necessarily bigger. Just like a plus b absolute value is less than or equal to absolute sum of the absolute values of a plus b. It's a natural thing. But what do we know about this? The value of f, they're always less than or equal to 1, right? So that's less than or equal to 1. If x were a positive number, that covers this spot. So not only this Euler method is trapped in this two line, the actual solution that we don't know how it looks like, that actual solution is also trapped in between and here. It'll never go outside y equals x and y equals negative x. In particular, all these values of a zx and all these values of xk and yk, they're all trapped in this entire box in particular. It's actually trapped in between these two lines. All right? So that no matter what we do, as long as we're in this box, No, it's how many times you divide it through, all those xk, yk's are always guaranteed to be in this box, and therefore we can use this maximum, minimum, and can kind of control the values in there. All right, that's the weird part of this solution. The rest of the part is more reasonable. So the next thing is actually we write down these two values, yk plus 1 and yk plus h times f of xk. What is f of xy? Is it xk plus, was that 1/2? 1/2 was there. 1/2 times xk yk squared, right? That's what f of xy was. Right? So this is Euler's method, correct? And z of x is actual solution. And we have all these points, x1, x2, all the way up to xn. I'm going to call zk to be the value of this actual function at that point xk. Is that right? So if we go back, these are the actual solution. And we have lots of points, x1, x2, all the way up to xn. I evaluate those points at actual solution, and those are zk values. And I want to compare that zk with this one in here, which is zk plus 1. Okay? So how I'm going to compare gk plus 1 and the gk in this fashion. This came from Taylor series, right? So I'm going to look at the Taylor series of zk, but you may or may have not seen this formula before. You might say, oh, I've seen that before, but there's a subtle difference in there. I want you to point that out. This is not a Taylor polynomial. It ended it here. Because of that, it is not a Taylor series. Probably it's going to be a Taylor polynomial, but I claim that this is not a Taylor polynomial. What's different about this one? Yeah, x star is in there. If this were a, that's just Taylor polynomial, right? And this equal symbol would be wrong. It's approximate, not equal, right? But there's a remainder theorem that is also part of that analysis in Calc 2, that there is some value. You can plug it in there instead of a, in between a and x, and this x value in here, such that this actually becomes equal symbol. This is either integral value of mean value theorem or intermediate value theorem. You can use that argument to show that there is a value. You can stick it inside the second derivative such that these two things are equal to each other. So this is a good thing to use to analyze it. So if you plug in xk plus 1 here, then that becomes k plus 1, zk plus 1. And if you plug in xk in a, then it's zk. And z prime of xk, and that is equal to f of xk, zk in there, and plus z prime of xk star is a probably right notation for 2 divided by, if I plug in, I forgot h in there, that's h. This is x minus xk, with x being xk plus 1, that becomes h squared in there. So you can compare the zk plus 1 with the zk, and that is analogous to that one. So this is the explicit part, which is x 1/2 times xk plus zk squared. That came from the definition of fxy in there. Then this is a problem, zk double prime. All right? So here's the second exercise. We have practiced one, actually, believe it or not, today, that writing this z double prime of x in terms of x and z, that's your second exercise there today. So here's a hint. What do we know about z? We don't know how it looks like. We only know about the differential equation, right? What is the differential equation? Z prime is 1/2 times x plus z squared. That was the differential equation that z satisfies. And we have this z double prime in our analysis. We want to do something about it. So I want you to go ahead and figure out what z double prime is going to be here. If z prime is equal to 1/2 x plus z squared. Alright, how was it? If you differentiate the equation one more time, you will get to z double prime. So left hand side is going to be z double prime, and it's a derivative with respect to x. I'm differentiating this one. X is the main variable, it's 1. Z squared is a 2z, right? But it has to be z prime there. It's a chain rule. But z prime is again this expression, so you can entirely turn this one into in terms of x and z. So this expression in here can be replaced with this expression with xk star in it. Alright, so let's write that down. What is zk plus 1? Is a zk here plus this expression is 1/2 times xk plus yk zk squared h plus 1/2 of this expression z double prime xk star is replaced with this one with xk star and xk star plugged into this z. So let me just write it that way. Xk star z with this xk star plugged in there plus z cubed in there. And here's h squared. Alright? So we don't know what zk exactly is, but it has that shape, and because these are all inside the box, we can just replace that with that size of whatever the maximum value that contains, because all xk's and z are trapped inside that box. That's why we don't need the exact value. It can be replaced with the m's and mk's and m1's and m2's. So we're going to subtract these two, and then you have this difference of this one and difference of that one, and something nice happens. Was there a question? Yes. Alright, so let me copy that and write down and go from there. No. I think it did save though. Right. Copy it there. So let me write down it over here so that you can compare that with the zk's. Yeah. So this is how it compares yk and yk there, and h and 1/2. These had the similar shape because it's a Taylor polynomial, and this was extra term. So we're interested in difference between these two, so I'm going to subtract both sides together like this: yk minus k plus 1 and zk plus 1. Is that right? If you subtract these two, you have yk minus zk. They're in a similar shape. We're interested in these terms. How different is it? Plus, there's a 1/2 and h. They are common there, right? And you see that xk, they're the same. If you subtract it, they go away. What's left here is yk squared minus zk squared. Fair enough? And then this one will be negative 1/2 of these values. Good? So since we're interested in this one, I'm going to call that one gk, gap between the approximation and actual value. Therefore, this one is going to call gk plus 1. Fair enough? So we have this new equation. Gap, after repeating k plus 1 times, is the gap from the k iteration of the Euclid's method plus these quantities. So I'm just going to copy that part. All right? And next part is that changing this one slightly to the factor. Obviously, you see this factor, yk plus 1 and ck. Yk is trapped in between 1 and negative 1 because of that box condition. And zk is also trapped in between negative 1. So this is under control, but you have this one showed up again, and that's gk again in there. And that's a crucial part. And these are all trapped inside, so we can rewrite it in a different way. if I put the absolute value, this is what we're interested in, absolute, how different is it, and replace this one with the larger value, so therefore we're entering greater than, and this one, if you put absolute value all around, it's going to be smaller than absolute value of this one plus absolute value of that one plus absolute value of that one. So this is where I'm entering GK there, and plus all these things, 1/2 h is usually a positive number, and this is GK now. And this one is absolute value of YK plus ZK. Plus, you can put that negative inside the absolute value. It's 1/2 there, and of that one. Okay? Now, further replacing this one with the maximum value, here it is, GK plus 1/2 h. I'm keeping that GK there. What is the maximum value of this one if everything is trapped in between this box? Negative 1 down there, positive 1 up there, there. These are y coordinates, and zk is also y coordinates in there. They're varying in between 1 and negative 1, right? It's a maximum of 2. 2 is the maximum you get absolute value, so 2 is replaced. The maximum value yk 1, maximum absolute value of zk is also 1, so they're trapped in here in terms of 2. How about this guy over here? 1, x coordinate trapped in between 0 and 1. Z coordinate, no matter what, is trapped in between 1 and negative 1, so that's 1, 2. And z cubed 1 as well. So all these unknown parts gone, so we have this quantity that everything is known as GK. If you factor that out, it's 1 plus 1/2, and 2 and 2 cancel, is 1 plus h, plus this is 3, so the 3 over 2, h squared. Alright, so the gap at the k stage, the k plus 1 stage, is less than k, gap at the k stage plus this number and that number. As k varies, this never changes, right? H is 1 over n, k varies from 1 through k, 1 through n. Right? So here's what happened with this quantity. What is G0? It's at the beginning of the gap, so we start at the right point, so this is 0, correct? Yeah. This is y0 minus z0. They're set to the same value. After that point is a different. So let's try G1. What is G1 here? When k equals 0, you get g of 1. So plugging k equals 0 there. That's G0. And it's 1 plus a. So I'm going to call that one capital A. And that's capital B for simplicity. And A plus B. And what is g of 0? That's 0. So that's only B here. Okay? So let's try G2. This is when k equals 1. Then if you plug it in there, that's g of 2 and the g of 1. And A's there and B's there. But we know about G1. G1 is less than B, right? So we can replace that with B there as well. Let me put the B in front. Let me factor out B there, and then you have A plus 1. And if I see one more time, you will see the pattern. G3, and k equals 2 there. If you plug in 2, you have G3. So that's G2, 1 less, and A plus B, right? But what is this G2 less than 2? Is this quantity. So there's a B and A plus 1 and plus B there. There was A out there. B. So B is all common. B factored out. What are you left with? A squared plus A plus 1, I think. Agree? Yeah. Let me do one more time. Why don't you go ahead and guess it for us before we work that out? All this thing is going to be, B is going to be always out there. Anybody? A to the third plus A squared plus A plus 1. That's actually the correct answer. Let me write that down. 1 less, G3, A plus B. Now G3 is replaced by this one, B times A squared plus A plus 1 times A plus B. You factor out B, and you can see that's exactly like this. All right? So let me write down Gn. This is our ultimate goal. Anything Gn? This is a gap at the very end, right? This is less than or equal to this one in here, B. What is the correct power, you think, to start with? If it is a 4, start at 3. If it's 3, start at 2. So it starts at where? N minus 1, N minus 2, all the way down to a plus 1. All right. Here's the ultimate question. Who remembers the formula for this geometric series? That's not the answer. Oh, obviously responding to all part. Yeah, this is a sum. Goes like this. There is a common ratio a minus 1. And what was the numerator? Was a to the minus 1. What is the right power there? And that's the number of terms. How many terms are there? N terms. You put n terms there. So that was the answer. All right. So if you look that up, geometric series, that n sum with a dot 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 and close into this part there. All right. Okay. Let's go plug back in there. What's B? B was this 3/2 h squared, right? Fair enough. That was B. And what was A? A was 1 plus h, right? It's 1 plus h. There, very nice. Cancel out. And here's 1 plus h raised to nth power, correct? So this is just h, right? Therefore, h cancel gives you this number right there. And you're left with this quantity, 1 plus h n minus 1. So the gap is less than that. The final bit is that this number here, which is written like this, 1 over n to the n. Does anyone know what happened to this quantity as n increases? This one approaches what number? Not 1. Not infinity. Infinity is a problem, right? We want to control it down, so that's a problem. It's got to be some number. It's actually English letter. No, it's English letter. E. E was the answer. Remember that part? That's the actually very definition of E. Yeah, the infinite series. All right? So it's actually less than E. It actually increases toward to E. So I can say this is definitely less than this one times. That one is always less than E minus 1. That's the gap. The gap, without even knowing the actual solution, is just proven to be less than equal to this quantity, where h is 1 over n. So what happened to this part? As we chop that box into many, many pieces, this one goes to where? This time it's not English letter. This is a number. E minus 1? What happened to E? As n approaches infinity, nothing else is in there. Approaches 0. That's what we wanted. The gap at the end eventually approaches 0. Alright? This is how mathematicians explain why. Alright. You probably won't never see things like this ever again in this course. But this is, when I do the Euler's method, I feel like a lot of things come into play in here, right? And this legit question, why does it accurately measure? And one explanation that involves a lot of things you have learned. And I thought it's a fantastic thing to share Friday afternoon. All right?